Stranger Things. Season 5 just ended, and the internet is losing its mind over the finale. The Upside Down, this dark mirror dimension sitting right next to our world, separated by nothing but a thin barrier that kids can rip open. It's fiction. Obviously, except for one problem. Physicists stopped being comfortable laughing at this idea. For 70 years, suggesting that parallel universes might actually exist meant stepping outside what most scientists were willing to take seriously. It was science fiction. It was fantasy. It was the kind of thing that didn't belong in peer-reviewed journals. But something changed. Not because we found proof, not because someone opened a portal in their basement, but because every single time we tried to explain how reality actually works, we kept running into the same uncomfortable possibility that maybe reality doesn't behave like a single universe at all. And once you start taking that seriously, fiction starts feeling a lot less fictional. The Scientist. They laughed out of Princeton. In 1957, a graduate student at Princeton University named Hugh Everett had a problem. He was studying quantum mechanics, which is the science of how really tiny things like atoms and electrons behave. And the more he studied it, the less sense it made. Every experiment that physicists ran kept showing the same bizarre result. Particles were doing things that should be impossible. They were acting like they existed in multiple places at the same time. They were behaving as if reality itself couldn't make up its mind about what was actually happening. Now, most physicists at the time had a pretty simple explanation for this weirdness. They said that particles exist in all possible states at once until you look at them, and then reality collapses down into just one outcome. The act of observing forces the universe to pick a lane. This is called the Copenhagen interpretation, and it was the standard explanation that everyone used because it worked well enough to predict what would happen in experiments. But Hugh Everett thought this was ridiculous. Why would reality care if a human was watching? What makes observation so special? So he came up with a different explanation. He said that reality doesn't collapse at all. Instead, every single time a particle has to make a choice between multiple states, the entire universe splits. Both outcomes happen. You just only see one of them because you're stuck in one version of reality, but the other version is just as real, and it's happening right now in a parallel universe that you can't access. This is called the many worlds interpretation. And when Everett presented it to his professors at Princeton, they absolutely hated it. His thesis advisor told him the idea was too wild to publish. Other physicists said it was philosophy, not science. Some people thought he was just making stuff up to sound clever, and the whole academic community basically told him that if he wanted a career in physics, he should probably shut up about parallel universes. So that's exactly what he did. Hugh Everett left academia. He went to work for the Department of Defense doing weapons research, and he never published another paper about quantum mechanics for the rest of his life. He died in 1982, mostly forgotten by the physics community. His idea should have died with him. Except it didn't, because even though people hated the many worlds interpretation, nobody could actually prove it wrong. The math worked perfectly. It explained every weird quantum result without needing any special rules about observation or consciousness. It was clean, it was elegant, and it refused to go away. Other physicists kept coming back to it because every alternative explanation had problems that were even harder to swallow. When reality started breaking the rules. Here's the thing about quantum mechanics. It's not just weird in theory, it's weird in practice. Like really, really weird. And the more experiments we run, the weirder it gets. Let me give you an example. There's this famous experiment called the double slit experiment, and it's been freaking out physicists for over 100 years. Here's how it works. You shoot a single particle, like an electron, at a barrier that has two narrow slits cut into it. On the other side of the barrier, you have a screen that detects where the particle lands. Now, logically, the particle should go through one slit or the other, right? It's a single particle. It can't be in two places at once. Except that's not what happens. When you run this experiment, the particle creates an interference pattern on the screen. That's a pattern that only shows up when waves overlap with each other. which means the particle somehow went through both slits at the same time and interfered with itself. A single particle acting like it's in two places at once. That's not supposed to be possible. But wait, it gets worse. If you put a detector at the slits to watch which one the particle actually goes through, the interference pattern disappears. The particle suddenly acts normal again and only goes through one slit. It's like reality changes its behavior depending on whether you're watching or not. This is what physicists have been dealing with for a century. Particles that refuse to follow the rules. Then there's Schrödinger's cat. You've probably heard of this one. It's a thought experiment where you put a cat in a box with a device that has a 50-50 chance of releasing poison. According to quantum mechanics, until you open the box and look, the cat is both alive and dead at the same time. It exists in a superposition of states. Only when you observe it does reality pick one outcome. Now, most people hear this and think it's just a metaphor, but it's not. This is literally what the math says happens. And we can test it with particles. We can put electrons into superposition where they're spinning clockwise and counterclockwise at the same time. We can measure it. We can use it to build technology. Superposition is real. And then there's quantum entanglement. This is when two particles become connected in such a way that measuring one of them instantly affects the other, even if they're on opposite sides of the universe. Einstein called this spooky action at a distance because it seemed to violate everything we know about how information travels through space. But it's real. We've tested it thousands of times. Particles really do stay connected across impossible distances. So here's the problem that physicists ran into. Every single one of these experiments suggests that reality doesn't work the way we think it does. And the standard explanation, the Copenhagen interpretation, basically just says, don't think about it too hard. It says particles are in all states at once until you look, and then the universe magically picks one. But that raises a huge question. What counts as looking? Does it have to be a human? Does a camera count? What about a bacteria? Where's the line? The many worlds interpretation doesn't have this problem. It says the particle goes through both slits. The cat is both alive and dead. The entangled particles are connected across all versions of reality. Every outcome happens. You just only experience one branch of the multiverse because that's the one you're in. It's not magic. It's just math. And the math works perfectly. When the impossible became normal. So if the many worlds interpretation has been around since 1957 and the math works, why did it take so long for scientists to start taking it seriously? That's where things get interesting. Because what changed wasn't the evidence. What changed was how comfortable physicists became with uncomfortable ideas. Back in the 1990s, if you polled physicists about which interpretation of quantum mechanics they believed, only about 5% would say many worlds. Most of them stuck with Copenhagen because it was familiar and it worked well enough for practical purposes. But if you run that same poll today, many worlds is now one of the top 3 most popular interpretations. Some estimates put it even higher among younger physicists. So what happened? Did we discover new evidence for parallel universes? No. Did someone figure out a way to test it? Not really. What happened is that science changed in a way that made the idea less scary. For one thing, quantum weirdness stopped being theoretical and started being useful. We now have quantum computers that deliberately put particles into superposition to run calculations. These aren't just lab experiments anymore. Companies like Google and IBM are building actual quantum computers that use the fact that particles can be in multiple states at once. They're using the weirdness to solve problems that regular computers can't handle. And here's the thing about quantum computers. They work by putting quantum bits, or qubits, into superposition. A regular computer bit is either a 0 or a 1, but a qubit can be 0 and 1 at the same time. And when you have multiple qubits all in superposition together, they can explore multiple solutions to a problem simultaneously. It's like having thousands of parallel computers all working on the same problem at once, except it's all happening inside a single machine. That only makes sense if particles really can exist in multiple states. And if particles can do it, why can't entire universes? We have encryption systems that use quantum entanglement to secure data. Banks and governments are investing billions of dollars into quantum cryptography because it's theoretically unbreakable. You're trusting your money to technology that only makes sense if particles can be magically connected across space. Chinese researchers have already launched satellites that use quantum entanglement to create secure communication networks. This isn't science fiction. This is happening right now. GPS satellites have to account for the fact that time moves differently depending on your speed and altitude. That's Einstein's relativity, which is another type of physics that used to sound completely insane. The idea that time itself can speed up or slow down depending on how fast you're moving. That should be impossible, but it's not. And if your phone's GPS didn't account for it, your maps would be off by miles. Every time you use navigation, you're relying on physics that violates common sense. Weird physics isn't philosophy anymore. It's technology that you use every single day. Your phone, your internet security, your navigation systems, all of it relies on physics that violates common sense. And when the impossible becomes normal, you start getting more comfortable with other impossible-sounding ideas. There's also been a generational shift in physics. The scientists who laughed Hugh Everett out of Princeton in the 1950s are mostly retired or dead now. The physicists running labs today grew up in a world where quantum computers and entangled particles are just facts of life. They didn't have to unlearn decades of classical physics training. They started their careers already comfortable with the idea that reality is fundamentally weird. And science communication changed too. YouTube channels explain quantum mechanics to millions of people. Podcasts break down the double-slit experiment for commuters stuck in traffic. Twitter threads about Schrödinger's cat go viral. The average person today has more exposure to quantum physics concepts than professional physicists did 50 years ago. That cultural familiarity matters. It makes the ideas feel less alien. And then there's the cultural shift from pop culture. Stranger Things, Everything Everywhere All at Once, the Marvel Multiverse, Rick and Morty, Spider-Man, Into the Spider-Verse. The idea of multiple realities existing at once has gone from fringe science fiction to mainstream entertainment that gets billion-dollar budgets and Oscar nominations. Everything Everywhere All at Once won Best Picture at the Academy Awards. A movie about the multiverse beat out traditional dramas for the highest honor in film. When you grow up watching stories about the multiverse, when you see characters jumping between parallel dimensions as casually as they'd cross the street, the concept stops feeling alien. It becomes familiar. And that familiarity makes it easier for scientists to talk about many worlds without feeling like they're going to get laughed out of the room the way Everett was. But here's the most important thing. The alternatives to many worlds keep getting harder to defend. If you don't accept that reality splits into parallel universes, then you have to explain why observation is special. You have to explain why particles act like waves until you look at them and then suddenly collapse into definite positions. You have to explain quantum entanglement without allowing faster-than-light communication, which would break Einstein's relativity. Every single alternative interpretation has to add extra rules and special cases to make the math work. You have to say things like, observation collapses the wave function, but only sometimes and only for certain types of observation. And we're not really sure what counts as observation, but trust us, it works. That's not satisfying, that's just pushing the mystery around. Many worlds doesn't need any of that. It just says the universe does everything that the math allows, and we only see one branch of it. That's it. No special rules, no magic, no arbitrary cutoffs where quantum mechanics stops applying and classical physics takes over. Just infinite parallel realities, splitting off every time a quantum event happens. And for a lot of physicists, that started sounding less crazy than the alternatives. So the shift that happened wasn't about proof. It was about comfort. Scientists went from "this is too weird to accept" to "this is the least weird option we have." And that's why Hugh Everett's idea that got him pushed out of academia in 1957 is now being taught in university classrooms as a legitimate interpretation of quantum mechanics. The evidence didn't change. We just stopped being scared of where the evidence was pointing. Why we still can't open portals, but here's where we need to pump the brakes. Because even if many worlds is correct and parallel universes actually exist, Stranger Things still gets it completely wrong. And this is important because the difference between real physics and science fiction is huge. In Stranger Things, the Upside Down is a mirror dimension that exists alongside our world. Same place, different reality. And there are these gates that you can open to move between them. That's not how many worlds works at all. Not even close. In the many worlds interpretation, parallel universes aren't sitting next to each other like floors in a building. They don't exist in the same space. They split off from each other every time a quantum event happens, and then they're separated by something called quantum decoherence. That's a fancy way of saying that once universes split, they can't interact with each other anymore. There's no going back. There's no portal you can open. The other versions of reality are completely inaccessible. Think of it like this. Every time you make a decision, the universe splits. In one universe, you turned left. In another universe, you turned right. Both versions of you are real. Both are happening right now. But those two universes can never touch each other again. You can't visit the version of yourself that made the other choice. You can't communicate with them. You can't even prove they exist. They're separated from you by the fundamental structure of quantum mechanics. So if parallel universes exist in the many worlds sense, they might as well not exist for all the good it does you. You're stuck in your branch of reality forever. No portals, no travel, no way out. But wait, there is one other possibility. And this is where physics gets really speculative. There's this thing called a wormhole, also known as an Einstein-Rosen bridge. It's a theoretical tunnel through space-time that would connect two different points in the universe. If wormholes actually exist, and if you could somehow keep one stable, then theoretically you could use it to travel vast distances instantly. Or maybe even travel to parallel dimensions if they exist in a different way than many worlds suggests. The problem is that wormholes require something called exotic matter. That's matter with negative mass. And we've never found it. We don't even know if it can exist. Every form of matter we've ever discovered has positive mass. Negative mass would behave in completely bizarre ways. It would fall up instead of down. It would push away from gravity instead of being pulled in. It's theoretically allowed by the equations of general relativity, but that doesn't mean it actually exists anywhere in the universe. So even if parallel dimensions are real, and even if wormholes are possible, we'd still need to discover a type of matter that we've never seen before and figure out how to use it to hold open a tunnel through reality. That's a lot of ifs. And every single one of them is a massive scientific challenge that we're nowhere close to solving. This is why Stranger Things is still science fiction. Not because parallel universes are impossible, but because accessing them is impossible. Or at least impossible with everything we currently know about physics. Here's what actually happened. In 1957, a grad student proposed that every quantum event splits reality into parallel universes. He got dismissed by the scientific establishment, and his idea was treated as wild speculation for decades. But the math kept working. The experiments kept producing results that were easier to explain with many worlds than with anything else. And slowly, over 70 years, physicists went from laughing at the idea to considering it one of the leading interpretations of quantum mechanics. That's the shift. Not proof, not evidence. Just a slow realization that reality might be stranger than we're comfortable admitting. And that's why Stranger Things suddenly feels less comfortable as fiction, not because the show predicted real science, but because science started sounding just as strange as the show. We still can't open portals. We still can't visit parallel universes. We probably never will. But the idea that they might exist, that every choice you make creates a new branch of reality where a different version of you is living a completely different life, that's no longer something that gets you laughed out of the room. It's a serious scientific idea that some of the smartest physicists in the world are willing to defend. And maybe that's the most unsettling thing of all. Not that Stranger Things might be real, but that reality might be just as impossible to understand as the Upside Down. And we're only now starting to accept that. So, what do you think? Are we living in a multiverse where every possible version of reality exists somewhere? Or is many worlds just a mathematical trick that helps us make sense of quantum weirdness without actually representing how things really work? Let me know in the comments. And if you want more videos breaking down the science behind your favorite shows and movies, make sure to hit that like button and subscribe. Because reality is stranger than fiction, and we're just getting started.